Can everyone hear me back there? Okay. Okay. Okay, so I'm Bobbi Jo and do the applications for the NIRSC. Been with them since 2015. And before that, worked at a commercial forge lab for about 9 years, building calibrations there. So just keep in mind the things that Philip just went over was a good way to lead into this one. And some of it will be kind of a review, but in maybe a different way. So NIR, we all know what it is and why we use it. But the real thing is that a lot of the operators don't actually have a technical background in it. So it is a complex technology to understand, but it can be easily understood if you look at it a certain way and what you need to know versus what isn't applicable. So if it's used appropriately, it should be recognized as a valid testing method. And sometimes you'll run into naysayers, but hopefully after these presentations, you'll have some ammo to defend yourself. So when we talk about current limitations, so I think when you break it down into these three things, the lack of understanding the technology itself, what are its actual capabilities and why is it working that way, limits in the communication and data, how do we even get proper training for this? My journey through the industry has been a lot of finding somebody who knew something and learning from them, finding somebody else who knew a different part of it, learning from them. It's not something you can just Google usually. Inconsistencies in data reporting and data use. We'll go over that a little bit here. And differences in forge calculations. This group has talked about that before, but just some things to keep in mind and aware of when you're comparing data sets. And then limits in uniform instrumentation. I'm not really speaking on our good benchtop instruments here, but when you're comparing them to the handhelds, I'm going to talk about wavelength range, why that's important, and how the sample presentation is important. The question you had back there about the distance, so when you think about a handheld, they advertise them as point and shoot. Well, you could have a lot of light, potentially contaminating that reading. You're not really getting a consistent scan on those samples, and just a different way to look at some of these different instruments. So I think if you break it down into these three simple things, you can have a much better understanding of how to use it appropriately. Without having to memorize all the technical stuff we just went over, if you know the very basics of spectroscopy. Spectral results from the interaction of light and matter. Okay, so knowing that, we know why moisture content and grind size are very important in regard to the light and matter it's reading. So understanding what can and cannot be done by NIRS based on the bonds and what we learned from Philip about their movements and how those are detected. And then different areas of the spectrum coincide with different analytes, and I'll give some examples of that. Very basics of calibration development we went over, spectra paired with a known value of reference chemistry, and the calibration data sets are built with actual samples. So therefore, to analyze one like it, an unknown sample, there must have been one like it in that data set that you use to create that calibration. And that sample range creates robustness in calibrations. Always comparing like to like, prepared the same way as those in the data set, scanning samples that are prepared the same way. Chemistry method for comparison must be the same as those in the sample set, and reported values are in a like format used in comparison. And we'll go through that in a bit here too. So again, here's the electromagnetic spectrum. So roughly 780 to 800 to 2500 nanometers is what we're looking at here with NRS. But the range that we typically use for forage is 1100 to 2500 nanometers. And why is that? So here's a typical spectra of a grass hay sample at that wavelength range. Now just kind of take a mental picture of this and where these peaks lay for the next slide. So, oh shoot, it doesn't say it. Okay, so if you can see down on the below here, it says 1100 to 25 nanometers. So both the top and bottoms coincide with that. So on the top, it will show you the bonds as Philip was explaining in his presentation, but then like kind of a histogram bar graph on what is showing up at those particular spots in the spectrum. So you can see there's quite a bit. You've got, this is almost right at 1100 here, a big protein peak. A lot of your fats. Let's see. Here, proteins again, you have several protein peaks. You can see lignin, cellulose, so those are important, for detecting all our fibers and fiber digestibility up here in these higher ranges. I'd like to point out that a lot of the handhelds do not have detectors that can go up that high. So when you think about, you need to look at, okay, what wavelength range is this instrument actually giving me? And why don't we use the lower range of the near-infrared portion? So this is that lower range. You can see there's far less information here. So this is about 740 to 1,000 nanometers. You have some fats and oils, and this can be used, this is extensively used for other things besides forage of importance, but for us, you can see there's way less information here. And this is a typical spectrum of that 850, the larger range. So, okay, why cut this out? Well, you can see this swoop here compared to the rest of the spectra. There's not a lot of information. You can see this little blip here. In this particular instrument, this is where the detectors switch. So keeping that in might add some variability into your calibration or create some noise there. So just one more reason when you're looking at forages, be aware of your instrument, where those segments are for detectors, and wavelength range. So with the consortium, we support mostly bench tops that would all cover that range. These are the list of our supported instruments, some of the older FOSSes still, and then their newer models. KPM has the XTs, and Blue Sun the Phoenix instruments. So all of these have appropriate wavelength range and appropriate sample presentation for scanning. It's a fixed way to scan. You just place the cup and scan. So again, the handhelds, why there's limitations in accuracy. They are great for red flags if you need minimal accuracy, but just an indicator on something. But often they don't have the optimal wavelength range. For example, one of the popular ones on the market is only 950 to 1650. Well, if you think back to this slide, they're missing a lot of the information at that other end of the spectrum where fibers and things like that would show up. Sample presentation is so variable, and then there's still moisture in the sample. We'll talk about that a lot, I think, in the next presentation. So NRS based on the bonds, like we talked about earlier, especially good at picking out carbon, hydrogen, oxygen, nitrogen also. But when there's too much moisture, it'll create a large peak at those water areas, and then kind of mask the other features of the spectra in that wavelength area that would be specific to other components. So I apologize, the bottom spectrum here isn't showing up real well, but this is the same sample, one at 91 dry matter, the top one's at 91, bottom at 96. You can see those huge peaks where the water is still in the sample, and you can see that it's not consistent throughout that spectra. So like right here, it's really masking some things here when that huge peak is in there. So we recommend the optimal range for scanning is a residual dry matter of about 94 to 96.7. And then next, what about this new analyte? Can I try this with NIR? You get a lot of questions about this. So things to question when you're thinking about what this technology can be used for. Okay, first think of the organic structure in regards to bonds that we talked about, and that complexity of that structure, and then the concentration of the analyte. Is there enough to even be detected? So when people talk about measuring something that would be like parts per million, parts per billion, I kind of shy away from that because that's almost getting to the range of not detectable. Then is the range of the analyte reasonable? That's another one, like if the range is too great, where you could never possibly find a sample for that data set in each of those ranges, probably not a good fit for NIRS. And then can slight error in this analyte be dangerous to the animal? You always want to think about that when it comes to toxins, nitrates, and use the technology appropriately. So our other technical limitations. So knowledge of the calibration and calibration use. Are the samples prepared properly? Are we using the right product to scan? And then also understanding your software. Each of the instruments has slightly different software. Scan settings, those are important, but might be overlooked often. It's how the sample cup you're using is presented and sample presented to the instrument, how many scans it takes and how. Understanding that some of the constituents are predicted values while other are calculated parameters. So those are applied on the instrument, not within the calibration. They're not actually a part of the calibration. So you need to monitor and update your calibration formulas. So understanding your predicted values. It's a secondary method, and for some reason, everyone just assumes there's no lab error in the chemistry reference method. They always take chemistry as being, no one argues with it, it's the golden standard. Well, there was lab error there in any of your samples that you've sent to the lab or used for your reference data set. So just being mindful of that lab error, and some labs will offer it to you if you ask, can you give me your lab error on NDF? In a way, you can do your independent validation and use that number to calculate standard error predictions. And are we even evaluating the correct variables to what we're trying to do? How many of us have heard, my results don't match the other lab I sent my sample to? A lot, okay. Why doesn't it work? Well, it probably is, but we're not looking at it correctly. So these are the common mistakes of independent validation. When you split your sample to send one to a lab and another, how did you do that? Did you do it correctly? Are they evenly split, or did you just grab one here and grab one there? Corn silage, it would be terrible to do this way. You'd get a handful of kernels versus a handful of stalk. So you need to do your splits right. That's number one. Comparing results on the wrong moisture basis. This sounds simple and everybody knows as is versus 100% dry basis, but it's not always clear when we're sharing spreadsheets and getting stuff from the lab. Just double check. It happens more than you would think. Comparing the wrong reported values, I've seen a lot of confusion with some of the fiber digestibility stuff. So NDF-D versus DNDF, insoluble versus soluble crude protein, and then NDF, as we've moved to the ash-free NDF. Some labs just say NDF, and it's actually the ash-free. So just being aware which one you're actually using. Comparing the different wet chemistry methods, there are biases against some of them, and I'm going to just point out NDF with the ANCOM versus AOAC methods on particular samples. And then if you are doing a true validation set, you should do some replicates at that lab. If you want to know the true lab error, you can calculate your own and know if what you're doing for validation is correct. Comparing the calculated parameters instead of the individual constituents. Again, different forage calculations. So if you don't know what your formula is, look it up, and then you can see which of those constituents was causing it to be higher or lower or whatever you're not expecting. And then applying a bias using too few of samples without enough range. If you do this on a handful of samples, it can lead to inaccuracies on the majority of your samples. Okay, calculated parameters we talked about, but this is the TDN example I have, just 2 of them. Oops. We have how many more out there? Yeah, so, okay, you get your TDN number from your NIR prediction. Okay, which one of these do we think is wrong? ADF, NDF, protein, fat, ash? I don't know, let's take a look and look at them specifically. They're not part of the calibration. And I don't know how many times I've come across an instrument where they've just gotten this handed down and they don't even know which ones they're using. They're just on the instrument and no one really checks it or wants to start comparing a different formula. Okay, so here's an example of that. So I took, now this is just random even numbers that I took that kind of made sense for these values. So say this was your predicted value for each of these: protein ADF, NDF, digestible NDF, and in vitro dry matter digestibility. So if I calculate RFQ and RFV using, I found several different formulas on actual members' computers, and I calculated a range. Well, those same predicted values produce this range, 141 to 163, and RFV 152 to 162. Now, this is by no means the most extreme sample. It's just I picked these even numbers. So just be thoughtful and mindful of what you're actually using and comparing. And then with your reporting clarification, these are the ones that most often get confused or mixed up or are abbreviated in a way that's not exactly like this and get mixed up. So in the consortium calibrations, we have IVT, DMD, which you can easily calculate your UNDF by 100 minus that. You can calculate, so your undigested NDF, digestible NDF, and in vitro dry matter digestibility. These are the protein ones that generally get mixed up, just to keep in mind. So biasing, we mentioned, and Philip mentioned too, it can lead to some tail chasing. If you're constantly biasing back and forth between different sets of samples, it can get bad. So proper validation set to find the true bias, that would include all the species, varieties, growing regions, and growing conditions, this would take a long time to collect even this set. So a handful of samples isn't enough. So in conclusion, general understanding of the technology and proper data use is key to success. And if you would like to know more about all of the proper ways and to do things, we have a guidelines document that we worked on for several years that outlines everything from sample preparation to the calibration use. It's a good resource to have and keep at the instrument for any technician coming on. And with that, I say thanks.
Any questions for what we did?
No.
You got one in the back there?
Yeah, I don't know if it's been commented, just a comment that actually I work with all the things for your statue, but just a comment is that I think another thing is like working with a lab has a bunch of it, and another thing is like you go to run samples. Let's say you're doing a project that has oats in it and grasses and alfalfa in it. Like just making sure you're actually changing the calibration every time.
Mm-hmm. Yeah. Thank you. You're welcome.
Do you have any other questions? Got one from John.
Just a quick clarification on that, splitting that sample for validation. Just give it a quick review. I know it's
David, do you have that in yours? Sample splitting?
I can add it to the slide.
Okay, we're going to add it into the next presentation.
Any other questions? Over here.
Just one comment. I think, when you're looking at splitting samples, that's what we see most of the errors. If you really want to try to compare samples that are from one lab to another, it's good to have a sample and you send it to a lab and request from that lab to send that sample back to you that is for one sample and then send it to a different lab. That way you have a better consistency of what the sample is actually being tested.
I'll just add to the reference labs that we use are Dairyland Labs in Wisconsin and Cumberland Valley Analytical Services in Pennsylvania. So if you sent something there for validation, you would know those methods are identical to the ones for the calibration.
One more question in the back?
Yeah, just, I like that comment on split example, and another one that keeps in mind what you're talking about is, let's say you have a bag of burlap sack with alfalfa and drying for a while, and the dryers just go to take that bag to the grinder. By the time you get there, all the seeds are like falling off the stems. So when you go to grab your bunches of alfalfa stems, and you get the seeds and you just take your first sample from, let's say, what's the first thing that comes out of the grinder, and your second sample, and what comes out of the grinder is totally different. When you tested that in our lab, that you get completely different RFQ, which is actually good. Because the formula down the road is coming from the doctor.
So when you're talking about sample splitting, are you talking about when they're already dried and ground or from raw, like from the, or both? Yeah,
Jonathan?
I mean,
I can see.
I'm thinking about, I'm sitting there with a half-gallon freezer bag, because I don't let my program tech enough to put a small grab sample. And we're sitting there with like a half-pound of material to pull from.
Mm-hmm.
And so, if to Dr. Lewis's point, you just send that same whole bag around, I mean, I think that grabs on my end from the, I don't know, we've had agents do this with nitrates where they're pulling from that one bag, making sub-samples and sending those off to nitrates.
Mm-hmm. I would recommend then grinding it drying and grinding it all and splitting it maybe with a riffles.
Round robin single.
Well, with that too, though, you can, have lab contamination. You don't know what happened to it when it left you. So it's interesting what can happen.
Probably not talking about sending around a half-pound sample.
No, but to your point, when it comes to, especially alfalfa, I do a lot of work with alfalfa. When I've seen that you put it in the oven, you get all the fall. What I usually do in that case, I do grind the whole sample, and then I put it to a set of seed to get it more even full sample. And I can send it to the lab that's more consistent to having different types of size. And then sometimes you can put it to a cycle mill to really get it really uniform.
That may be, it's part of getting a good sample for NIRS, but what I'm hearing here is a lot of this is just proper getting of a representative sample from the field farm. So all of these things are, the reality of life, these are going to shatter and form. So that's the whole sample and grind the whole sample and get it to a point where you can get it representative and homogenized. You're going to have problems if you get it in wet chemistry in the lab, just
And we have the same issues with farmers when we get a sample where they just pull it off the bale versus the probes. I mean, the probes make it a lot easier for a homogeneous sample, and they also get a better representation of what's going on in the bale.
I think that's something that we overlook a lot also when we grind it, is that we will sharpen blades on the grind. That's another issue that is very common, is that they keep grinding and grinding, and they become not dull, and then the pipe starts to.
And also the grinding rings, if you're using a UD mill, sometimes you stick your finger inside of an old grinding ring and it's almost smooth, and it shouldn't be like that.
And also in a commercial lab setting where you're doing a different type of sample each grind, especially like if you've just ground corn grain and then your next thing is something else, those particles are still maybe hanging in there, will fall in. So, being mindful of cleaning out the grinder between products at least, but every sample would be better.
Some companies advertise, like, you see the bale of hay there, and approach it with an NIR, and then I get a valley. Or even I just get a grab sample, put it on the desktop, and then I get a valley.
Mm-hmm.
Where's the consortium in terms of developing calibrations for hand-processed samples?
At this point, we're not, because we aren't happy with the accuracy that they give us. Now, if we had a way to have a handheld with the appropriate wavelength range, some sort of sample presentation, whether it be an adapter, that would help a great deal. But still, the wet versus a dried and ground sample is the obstacle there. So
currently, we're just not,
we're not.
doing that.
Yeah.
And I think that would introduce a lot of error into the
Yeah, we would.
sample
Yeah,
analysis.
it's conversations we have because we know the industry wants it, and we know there is a use for it. But at this point, we are not happy with, or feel comfortable, I should say, adding it into one of our supported instruments.